Okay, so here's the last one. And now notice these have like two little dots in them. That means they're kind of hard, but I don't think so. So anyway, a 3 kilogram rod of length M. Assume we're going to assume that this rod has uniform density. In other words, that it's got a uniform center of mass throughout. Okay, um, and so if I take this 3 kilogram rod like this, then I am going to place, and it is how long? 5 meters long. So I'm going to say this is at 0, and this is at 5. All right. Now, if I was going to balance this rod on a fulcrum like this, if I was going to balance the rod, right now, if it's uniform, I'd say the center of mass of the rod, I'd put that this has got to go at the center of mass to keep it balanced. I'd say that'd be at 2.5 meters. But we're going to put some more stuff on here. So right here at 2.5 though, I'm going to put the 3 kilogram mass. In other words, I'm going to take that center, I'm going to take the entire mass of this rod and say, all right, even though the rest of it does exist everywhere else around here, I'm going to put the 3 kilograms right here at 2.5. So on our scale, this is 2.5 meters, and here is my 3 kilogram mass. All right. Now then, at opposite ends is a 4 kilogram mass over here. 4 kilograms, and a 6 kilogram mass here located at the 5. All right. Will the center mass be near the 4 kilogram mass? Okay, so in other words, it's saying, hey, where do you want to put the fulcrum to keep this balanced? Do we put it over here or do we put it over here? That's what they're asking. That's what they're asking. Well, I say, since this, if this is the bigger kid on the playground, you're going to need to make this lever arm shorter, and we're going to learn about torque in a little while, which is just force times distance. Again, kind of like work, but this time it's a vector and it's torque. Yeah, we're going to put it near the 6 kilogram mass. Okay. At the center of the rod, why? Okay, where is the center of mass of the system? So now we have to find the center mass of the system is 2.5 with no mass except for the mass of the rod. So now we've got to find the center mass of the system. So here's how we do it. Now we could have placed this at 0 and made this negative 2.5 and this positive 2.5, and our calculation would still work out the same. But I'm just going to make it 0, 2.5. That's a 5 meter rod. 3 kilogram, that's a long rod. 5 meters? That's 45 feet. That's almost 50 foot. We don't realize what we're doing sometimes with these problems. But anyway, so here we go. Let's find the center of mass. So XCM, it's all in the x-axis again, so that makes it nice and simple. XCM is equal to let's just take a mass at a time. Mass of the rod, we got to throw that in there, and mass 3. So XCM is equal to M1 times 0 plus M rod times 2.5 plus M3 times 5 divided by M1 plus M2 plus M3. And so when I run the numbers, I get 4 times 0 plus 3 times 2.5 plus 6 times 5 divided by 4 plus 3 plus 6, which is 13. So of course I get 0 plus 7.5 plus 30 divided by 13. 30 divided by 13. I am lazy. Is 2.3 Are you wondering why I'm staring at this? Because we have to take into consideration the weight of the rod. Because we have to take into consideration the weight of the rod. So this 6 has to do more work. So it is at 2.3. I'm going to have to edit this a little bit. I want to take out that long pause. I'll just warn you, there's a long pause at the end of track 3 where I'm staring at, why is this 2.3 meters? Well, it makes sense. Because if I say the center of mass of this thing is right here, that's going to make a big difference. It's going to make a big difference. That's why those teeter-totter things are really, really heavy. Got a huge center of mass, so you don't have to move the fulcrum very far, depending on how large the children are at the other ends. Okay, out here. I think I salvaged that.